Welcome to Tales from the Periodic Table. I'm your host, Ron Hipschman, and today we're going to talk about the element tellurium. I have a sample of that element right here. Let me show it to you. There it is in my little vial right there. It's kind of a silvery, shiny metal. But let's get back to our slides. Here, you see the beautiful periodic table produced by Theodore Gray. Incidentally, Theo has written one of my favorite books called The Elements, which you can pick up from the online Exploratorium store if you want your own copy. Check out his fantastic website, periodictable.com. Tellurium is the 52nd element in the periodic table. Its atomic number is 52 because that's how many protons are in its nucleus, and that is what distinguishes it as this unique element. Tellurium-bearing compounds were first discovered within gold ore in 1782 by Austrian mineralogist Franz Joseph Müller von Richtenstein. He noted, when heated, the new metal gave off a white smoke with a radish-like odor. It's amazing that more chemists of his time did not sacrifice themselves doing experiments like that. He's celebrated in Austria with this postage stamp, and in Romania also with a postage stamp. Well, why Romania? Tellurium was discovered in a gold mine in Kleinschlatten, Transylvania, now Zlatna, Romania, a very picturesque town of about 7,500. Well, picturesque except maybe for that giant smelter on the hill. Since Müller von Richtenstein didn't give the element a name, it was Martin Heinrich Klaproth who 16 years later, in 1798, with full credit given to its discoverer, named the element after the Latin word tellus, meaning earth, hence tellurium. The universe produces about half of the tellurium in dying low-mass stars, with the other half produced in merging neutron stars. It was pretty exotic. A new paper, just published last year, however, proposes that neutron stars had far less influence in the evolution of elements in the universe. Here, you see each element square with a chart of its own, showing its growth over the age of the universe by various processes. Tellurium is here. I understand this looks complicated, but let's look at tellurium a little closer. The horizontal axis of this square represents time, from the Big Bang until now. The vertical axis shows the proportion of tellurium created by various processes. Most of the tellurium present today is believed to be produced in supernovae, the yellow area. Note that tellurium produced by dying low-mass stars, the magenta area, doesn't get started until a bit later. This is because low-mass stars exhaust their nuclear fuel much more slowly and last a long time before they start dying. Supernovae are very massive stars that use up their fuel quickly and die relatively young. About 1/5 or so of tellurium is produced in dying low-mass stars, the magenta region. Here are two examples, NGC 7027 and the Spirograph Nebula, both taken by the Hubble telescope. Low-mass stars, like our Sun, or maybe a little bit heavier, exhaust their fuel at the end of their lifetimes and expel their outer shells of gas and dust, forming what's known as a planetary nebula, because they resemble planets when looked at through a telescope. Recently, a team of PhD students identified spectral lines of tellurium in the infrared light from these planetary nebulae, confirming this mode of tellurium production. Atoms heavier than iron cannot be made in the cores of stars. Those reactions absorb energy. Heavy atoms are made by absorbing neutrons. And it's believed, and now observed, that these dying low-mass stars are huge sources of neutrons, helping fill in the periodic table beyond element 26, iron. On Earth, tellurium occurs mainly with gold, silver, copper, bismuth, and lead, and is mined as a byproduct. Tellurium is a slight impurity that's reclaimed from the cast-off sludge when purifying, mainly copper and lead. Treatment of 1,000 tons of copper ore typically yields 1 kilogram or 2.2 pounds of tellurium. As a matter of fact, the town of Telluride, Colorado, came into being in hopes of finding a strike of gold telluride. They never found enough gold telluride to make it worth their while, but they did find some veins of gold. The town name stuck. Here's what gold telluride, called calaverite, looks like. In another interesting mining story, in Kalgoorlie, Australia, gold rush miners threw away material they thought was a mineral like pyrite or fool's gold as they looked for the real thing, gold. This material was actually calaverite, or gold telluride, and was used to fill potholes and pave roads. Once this was discovered, it caused a second gold rush, well, actually a tellurium rush in Kalgoorlie, except that it was the streets that got dug up. The streets were paved with tellurium. How many minerals that contain tellurium, like this native tellurium? None are common enough for commercial extraction. Note, if you can, how many are associated with gold, silver, copper, lead, and bismuth. Tellurium is a member of the chalcogens. The elements in this column all share some similar chemical qualities. Tellurium is also considered a metalloid. It has the qualities of a metal, but also the qualities of a nonmetal. In the periodic table, generally speaking, metals are to the left of the yellow line and nonmetals are to the right. Tellurium straddles that line in qualities. Tellurium is silvery white and very brittle. If you hit it with a hammer, it shatters, so it lacks the malleable qualities of normal metals. The main suppliers of tellurium are China, producing 63% of the tellurium in the world, followed by the USA with 11%, virtually all of this through recycling. We have no tellurium mines. Then Russia, Sweden, Japan, and Canada. In the US, we import 77% of the tellurium we use. Tellurium is a technology-critical element. The American Chemical Society's endangered element list places tellurium as, quote, serious threat in the next 100 years, unquote. This rating indicates the relative risk to the supply of tellurium required to maintain our current economy and lifestyle. How common is tellurium? Actually pretty rare. It's the 40th most common element in the universe. There's none in the sun, none at all. It's the 32nd most common element in meteorites. And it's way down. It's the 78th most common element in the crust. Only 1 to 3 parts per billion in the Earth's upper crust, compared to 4 parts per billion for gold. The rareness of tellurium on Earth is probably due to its combining with hydrogen in the early cloud that formed the solar system. The hydrides of tellurium were volatile and evaporated from early Earth. Those remaining combined with heavier elements and sunk to the core of the Earth, leaving very little in the crust. We find no tellurium in the oceans and no tellurium within us, inside of human beings. The current cost of tellurium is about $64 per kilogram. Given its rarity, about the same as gold and platinum, it has a shockingly low price. Gold is about $60,000 per kilogram, and platinum is about $29,000 per kilogram. I suppose that's because of tellurium's brittle nature. You can't cast and hammer tellurium like you can the precious metals. Also, it's mildly toxic, so it doesn't make coins you'd want to carry around in your pocket. Besides, these coins would shatter if you drop them. If we compare the size of the tellurium atom to that of hydrogen, we'd see something like this. The tellurium atom is about 2.5 times the size of hydrogen. By the way, a picometer is a trillionth of a meter. Atoms are small. Here are the atom sizes sorted from largest, cesium on the left, to smallest, helium on the right. Tellurium is a smallish, mid-size atom. Each element has many different forms. For each specific element, the number of protons in the nucleus is the same. 52 protons for all forms of tellurium. But there can be different numbers of neutrons in the nucleus. All these different forms are called isotopes, and they're chemically identical to each other, but with slightly different weights. The number you see next to the chemical symbol is the total number of protons and neutrons in the nucleus. There are 37 isotopes of tellurium, and of these, there are 6 stable, non-radioactive isotopes. These 6 stable isotopes are found in these proportions in nature. You'd think that all these stable isotopes would make up all the tellurium in the universe, but just looking at these percentages, it's clear that's not true. These only total a mere 34.18% of the tellurium in existence. Well, what's going on here? To find the missing tellurium, you have to look at 2 of its radioactive isotopes, tellurium-128 and tellurium-130. They account for the rest of the known tellurium, 62.82%. Just for those 2. Now we have 100% of the naturally occurring tellurium. We'll see how this can be in the next slide. By the way, the word isotope comes from the Greek isos, meaning same or equal, and topos, meaning place, since all these various forms of tellurium occupy the same place in the periodic table. Of the radioactive isotopes of tellurium, these are the longest lived, and the ones with half-lives over 1 hour. More about half-lives in the next slide. Tellurium-128 has a half-life of 2.2 times 10 to the 24th years. That's 2.2 million years, or over 160 trillion times the age of the universe. This is the longest known half-life of any isotope of any element. Tellurium-130 also has a very long half-life of 8.2 times 10 to the 20th years, almost 60 billion times the age of the universe. You see that extremely little of these isotopes have had enough time to decay significantly. Tellurium is one of 3 known elements, the others being indium and rhenium, where the stable isotope is less abundant in nature than the long-lived radioactive isotopes. If you had 1 gram of pure tellurium-128, you'd only observe 1 atom decaying every 674 years on the average. So what's a half-life? This graph shows an exponential decreasing curve. As an example, say we start with 1,024 atoms of any isotope from the previous slide. I chose 1,024 atoms because it's a power of 2 and we'll be doing a lot of divisions by 2. Now if you wait 1 half-life, half of your isotope will decay, and you'll have 512 atoms left. If you wait 1 more half-life, half of that half decays, leaving you with 1/4 of the original 1,024, or 256 atoms. Another half-life, half again as many, 1/8 the original, or 128 atoms, and so on. After 10 half-lives, you'll have about 1/1000th of your original amount. By the way, notice there's 1 remaining atom after 10 half-lives. If you waited one more half-life, your remaining atom would have a 50-50 chance of decaying in that time. Tellurium is moderately dense at 6.24 grams per cubic centimeter. As a reminder, water has a density of 1 gram per cubic centimeter. I've put up a couple more densities for comparison. Iron is slightly denser than tellurium at 7.89 grams per cubic centimeter. Here's a graph of the elements from highest density to lowest density. When we do this talk at the Exploratorium, we have a set of blocks so you can feel density for yourself, but we'll have to wait to do this until we're back in the museum. Our set of blocks have a wide range of densities, with the densest at tungsten, to lead, to copper, to iron, to titanium, to aluminum, and magnesium. We also have plastic and wood blocks, but those are not technically elements. Again, tellurium's density, the magenta circle, is 6.24 grams per cubic centimeter and is the 55th densest element between iron and titanium. Tellurium has the 70th highest melting point at 450 degrees Celsius or 842 degrees Fahrenheit. Tellurium also has the 70th highest boiling point at 988 degrees Celsius. That's 538 degrees Celsius above its melting point of 450, a pretty small difference between melting and boiling. Tellurium is soft, even though it's brittle, with a hardness only a 2.25 on Mohs scale of hardness. In this chart of hardness, sorted from hardest, boron, on the left, to softest, cesium, on the right, tellurium is the 42nd hardest, or rather the 25th softest element. Tellurium is the 72nd best conductor of electricity. As a matter of fact, we should probably consider tellurium a decent insulator. It's the 77th best conductor of heat, again, probably a better thermal insulator than a conductor. We'll see in a bit, though, that tellurium finds its way into some interesting thermal devices. From our periodic table of the spectra, we see that tellurium displays a variety of emission lines, richer in the greens and blues than in the reds. Every element emits a unique set of colors, allowing researchers to identify even small quantities in a sample using spectroscopy. Tellurium, when placed in a flame, produces two different colors, depending on the temperature. Pale green when it's a bit cooler and distant from the flame, and pale blue in the hotter part of the flame. Both a bit hard to see here. Let's take a look at some of the major uses for tellurium. In spite of my misgivings when I began looking into this element, it does have some interesting applications. These are the primary uses for tellurium. The largest, by far, is in manufacturing solar cells, followed by thermoelectrics, alloying, rubber production, and other uses. Let's take a look at these. Cadmium and tellurium can be compounded into cadmium telluride thin-film photovoltaic modules. Unlike silicon solar cells that use thick, bulk slices of silicon, these only use a thin, vapor-deposited film, so they use much less material and are hence cheaper to manufacture. The thinness means that you can deposit the film on flexible materials, like you see here. This also adds some unique manufacturing possibilities over the rigid and brittle silicon cells. Currently, cadmium telluride is the only practical thin-film photovoltaic technology, with lower costs than conventional solar cells made of crystalline silicon. These thin-film panels also have the smallest carbon footprint, lowest water usage, and shortest energy payback time of any current photovoltaic technology. The company First Solar has announced a cadmium telluride panel with 22.1% conversion efficiency. Bulk silicon solar cells have reached as high as 26.1% conversion efficiency. That's about 18% better than thin film technology. This is an interesting, if not a little crowded chart showing the progress in efficiency of various photovoltaic technologies over time. The horizontal axis marks the passage of time from 1975 to now, and the vertical axis displays the efficiency of the various technologies. First Solar's best cadmium telluride cell is right here at 22.1% in 2016, and the best silicon cell is here, introduced in 2018 at 26.1% conversion efficiency. As you can see, things get more efficient over time as expected. Many of these are experimental and not commercial. Elemental tellurium is used in the metal industry as an alloying additive, usually at less than 1%, for steel and cast iron, copper, and lead alloys. Tellurium promotes corrosion resistance and improves mechanical properties and machinability. Tellurium has a major use in thermoelectric devices. A thermocouple, let me magnify that a bit for you, is a device that can change a temperature difference into a voltage. Normally, this allows one to measure temperature. This phenomenon is called the Seebeck effect. This can also be used to generate electricity from heat. This particular device does not contain tellurium, but other thermoelectric devices do. This device, called a Peltier cell, contains many bismuth telluride junctions and can be used to generate electricity in thermoelectric generators, as we'll see in a moment. Making one side hot and the other side cool generates electricity. Interestingly, these also work in reverse. If you connect them to a source of electric current, one side gets hot and the other side gets cold. This is called the Peltier effect, named after the French physicist Jean Peltier. These can be used to cool down small refrigerators with no moving parts, or you can use a Peltier cell to keep another electronic component like a CPU or a laser diode cool and efficient. But back to its power-generating uses. Bismuth telluride thermoelectric generators are important for deep space missions like the New Horizons spacecraft that recently visited the planet Pluto. You can't use solar panels that far out. The sun looks like a very bright star in Pluto's sky. There's not enough light to generate electricity that way. The electricity to run the spacecraft is generated thermally with a small nuclear power source which supplies about 245 watts of power at launch. As the spacecraft continues on its mission, the radioactive material decays, supplying less and less power until, in the late 2030s, the generated electricity won't be enough to power or heat the spacecraft. The same goes for the Mars Curiosity and Perseverance rovers. With both rovers' large power budget, solar panels won't do the job. It takes a lot of energy to do all that moving around. You need a small, nuclear-powered generator, here mounted on the rear of the rover. Curiosity's generator produced about 110 watts of power at the beginning of the mission. Here's the power generator waiting to be installed in the Curiosity Mars rover. It's called the Multi-Mission Radioisotope Thermoelectric Generator, or MMRTG. This is the stuff that makes it work. What you see here is a pellet of plutonium-238, not the stuff in an atomic bomb, which is plutonium-239. The pellet is not red hot because it was just taken out of an oven. It's red hot because it's so radioactive that the particle emission heats it to this temperature. 2 of these pellets are put into a cylindrical graphite impact shell, which also heats up to red-hot temperatures. And then 2 of those graphite impact shells are fixed inside a rectangular block called a general-purpose heat source. The purpose of all this is to keep the plutonium from escaping in the unlikely event that the spacecraft fails during or right after launch, and the MMRTG falls back to Earth. There's a very good chance that these precautions will prevent the spread of any radioactive material. 8 of those square general-purpose heat sources blocks are stacked inside the MMRTG. The fins, they get rid of excess heat not needed to keep the spacecraft systems warm. Small amounts of tellurium are used in the vulcanization of rubber and in detonators. The salts of tellurium are partly used to produce a grass green color in fireworks, though boron is cheaper and a lot less toxic. Tellurium can be used for the coloring of glass and ceramics. It gives a deep ruby red color, very similar to selenium and cadmium that you see here. By the way, I've extracted this slide from a wonderful poster on the compoundchem.com website. I highly recommend their site for hundreds of interesting graphic chemistry tidbits. Plan to spend some time there. Combinations of germanium telluride and antimony telluride are used in phase change materials as part of optical storage disks like this CDRW disk, or in novel storage materials such as phase change random access memory. Phase change memory eliminates many disadvantages of flash memory and is an experimental technology worth keeping an eye on. Tellurium has no known biological function. Tellurium and tellurium compounds are considered to be mildly toxic and need to be handled with care, although acute poisoning is rare. Humans exposed to as little as 1/100th of a milligram per cubic meter or less in air exude a foul, garlic-like odor known as tellurium breath. Tellurium is found in historical medical applications for the treatment of microbial infections prior to the discovery of antibiotics. Tellurium, or potassium tellurate to be precise, was first used medicinally in 1890 for the treatment of nocturnal sweating in patients with tuberculosis. This is no longer used. Early documentation in 1926 reports its use in the treatment of syphilis and leprosy, though we now have much more effective and less toxic antibiotics. We'll end today's talk with Mary Soon Lee's elemental haiku about tellurium. So rare here on Earth because you fled into space, cited by Hubble. Thank you for watching Tales from the Periodic Table. The next program in this series will examine another interesting element, and one you've certainly encountered, iodine. We hope you'll join us. This program, like all Exploratorium programs, is only possible because of donors like you. We know that this time is challenging, but if you can, help us keep educational content like this free and accessible to all by donating today at www.exploratorium.edu/connect. Thank you.